Hello, and welcome back to Shikshata. Today we're going to be looking at exponential graphs. So today we're learning about graphs of exponential relations, and you know that you are successful at these, you have successfully learned about these when you can graph very simple exponential relations using a paper and pencil if I give you, or if somebody else gives you their equations. And also when you can make connections and describe what are the connections between the different ways an exponential relationship can be represented. Some of those representations, when I say representations of an exponential relation, I mean a graph, but I could also mean the algebraic representation or even a table of values. To get our minds in the right idea, I'm a big fan of video games, all sorts of games. And in some video games, you play as a character that collects experience points. And the more experience points you have, the stronger you get. In fact, when you have enough experience points, you do something which is called, in video games, it's called leveling up. So you might be level 2 or level 3. And the higher your level, the stronger your character that you're playing as usually is, which means you can do cooler things, you can fight bigger monsters. And to collect experience points in these video games, the players usually have to defeat monsters or complete tasks or quests or something like that. This is a pretty standard model for many games, especially role-playing games. And in one game, if you wanted to reach level 5 in the game Balthazar's Gate 2, taking a look at this right here, what would your plan be? You're trying to reach level 5. Right now you're at level 0. You have no experience points and no levels. And these two tables show you, okay, you need 15 experience points to reach level 1. You need 45 experience points to reach level 2. And so on and so forth until you reach level 5. Now, if you are level 0, there's many different types of creatures or monsters that you can fight. You can fight a rat. He'll give you 15 experience. And it would be a fair fight if you are at level 0. The danger for you would be, it would be fair. But if you're at level 1, now you're a little bit stronger. So if you were fighting a rat at level 1, you'd be pretty safe. There's not really a lot of risk to you. If you're at level 2, 3, 4, or 5, it's so easy, it's trivial. You don't have to worry about defeating rats at all. Like, you would take care of them no problem. Whereas fighting a raccoon at level 0, now there's a medium danger level. And the higher the creature that you fight, a wolf, a bear, even a dragon, the danger level increases. Obviously, some creatures are harder to defeat than others. But the higher your level is, the easier it becomes. So if you wanted to reach level 5, remember every time you defeat a creature, you collect this many experience points. How would you plan? What would your plan be to get to level 5? Well, hopefully 10 minutes is long enough for you to think about. You can pause this and think about, what would your plan be. You should take about 10 minutes to do so. And one of the strategies that you might come up with, hopefully you've had enough time by now, is to fight one rat first, right? And that would be at level 0, a rat would be a fair fight. And that would give you 15 experience points. That's level 1. Now, to get to level 2, recognize that you need another 30 experience. So you might say to yourself, a raccoon gives me 30. And a raccoon at level 1 is a fair fight. So I'll fight a raccoon. Then to get to that'll take me to level 2. To get to level 3, I need 45 experience. Oh, I could fight a wolf. That'll give me 45. And that's a fair fight, so I'll fight a wolf. And then you could say, okay, well, now I'm at level 3. To get to level 4, I need 60. That's a bear, right? Then you can fight a bear, and that'll get you to level 4. And then recognize from level 4 to 5, you need another 75. And that means that you should fight a dragon. That's a fair fight. The whole time, you will be doing fair fights, and you will get all the way to level 5. But some people don't want a fair fight. So another strategy might be, strategy 2 might be, hey, Rats give me 15 experience points, and the first fight I do against a rat is fair, and then it's safe. I don't need to worry about dying. I don't need to worry about anything. I could just keep fighting rats. And all I would need to do is do that. 225 divided by 15 is 15. I just need to fight 15 rats. And I could get all the way to level 5 and never see a dragon. I could be at the end of this game and I'm super strong, and anything I fight will be either trivial or a safe fight. Now, which strategy you choose ultimately depends on what is your type of enjoyment. Do you like to challenge yourself and have fair fights the whole time? Do you like to speed run, or do you like to just go, have it really, really easy and get to the end as quickly as possible? That's up to you. I'm going to give you another scenario now and give you another 10 minutes to pause this and think about a different type of level progression. So if you want to reach level 5 in the game Balthazar's Gate 3, so this is the sequel, and hopefully the game designers have improved on some of their issues and stuff. Now to reach level 1, you only need 3 experience. It's much lower. To reach level 2, you need 9. To reach level 3, you need 27. To reach level 4, now you need 81. And level 5 is way higher, 243. And the monsters also, the creatures also give you different experience rewards. So take 10 minutes now to think about what would your plan be to get to level 5 if this was the level progression. So one of your strategies, hopefully you had enough time to really analyze this and come up with your own, and maybe you thought, ooh, like last time, let me kill some rats until it's trivial, until it's too boring, and then recognize that, okay, maybe I want to start having some fair fights. Maybe you decided to go for a wolf right away first, even though the danger is really high, because you can jump right away with 18 experience points. You would jump from level 0 all the way to level 2. And then you could start maybe taking some, other high danger fights, like maybe a bear. And once you kill a bear, maybe a dragon after that. And then going back to doing some of the easier ones. One common strategy would be to recognize that, hey, if I need 3 experience points to get to level 1, I could just fight a rat. And then if I need 6 more to get to level 2, I could fight a raccoon. And if I need 18 more to get to level 3, I'll kill a wolf. And doing so, and then a bear, and then a dragon. And doing so would just be fair fights all the way down. Exactly the same as we did in Balthazar's Gate 2. And the other strategy, just going the other way entirely, remember in the other strategy that we used in Balthazar's Gate 2, we said, oh, I could kill 15 rats. Well, how many rats would it take for you to get all the way to level 5? 243 experience points divided by 3 experience points per rat would be 81 rats. After you're done killing, even, at level 2, rats become super easy to kill. And at level 2, you just need to kill 3 rats. And then the other 78 rats, you're just like walking around one-shotting them, like it's so boring. Is that, any point even playing the game at that point? And so the question here to really consider is, which strategy seems more fun to play? And I think very obviously, the one where you have 5 fair fights instead of 81 really boring fights. So what I'll ask you to do at this point, again, is to pause this video to do this. Use a scatter plot, and you can copy down my axes if you like. And I want you to use to plot all of this level progression, the XP requirements for each level in the second game versus the third game. And I want you to connect your dots with a smooth curve or a line and ask yourself, what do you notice about those 2 graphs? And take 10 minutes to maybe do that. Okay, so hopefully you got a chance to make one of these graphs, both of these graphs yourself. You copy down these axes and plotted these points, and I'm going to do that for us now so you can see what that should look like. So Balthazar's Gate, for level 1, it requires 15 XP, and 15 would be somewhere around, maybe around here, right? halfway of 50 would be 25, a little bit less than that would be 15. 2, at level 2, you need 45 XP, so that would be a little bit higher. At level 3, we need 90 XP. That'll be a little bit higher than that. At level 4, we need 150. At level 5, we need 225. And that creates, they're not exactly in a line, although they do kind of look like they're in a line. It's more like a very slight curve. Like the requirements do get a little bit harder each time. And we can see that even these, the difference between these does get bigger and bigger each time, but not by too much. On the other hand, what does the XP requirements for Balthasar's Gate 3 look like? Well, for level 1, you only need 3 experience, which should be basically at the horizontal axis. For level 2, 9 experience. That's still less than even the level 1 requirement for the second game. So that's still like really, really low down here. For level 3, 27 experience. Okay, it's starting to get a little bit bigger. That would be about there, right? 25 would be here. 27 would be just a bit higher. For level 4, now we need 81 experience, and it's still easier, it looks like, than the second game to get this experience. And then finally for level 5, we can see that, whoa, now the experience jumped quite a bit to 243. Looking at this graph, is there anything that you notice? What do you notice about these two graphs? And this can be anything, really big or even something really, really small. The important thing is that you are really exercising your mind here to see if you can pick up any patterns so you can get better at picking up these patterns in the future. One thing that's, pretty obvious to notice, but something that we should be noticing nonetheless, is that both of these graphs are going up. As the levels increase, the amount of experience you need does increase as well. So both of them are increasing. Even though they are both increasing, we notice that there is a curve, right? Neither of them are increasing at the same rate. There is a slight bend to these graphs. But of course, the bend for the red graph, Balthasar's Gate 2, it's not really that noticeable. Whereas for Balthasar's Gate 3, it seems like there's a really, really intense bend happening around here. I wonder, what does that mean when there's a bend like that? Well, we can see here that the amount of experience required, as the levels are increasing, the amount of experience required is going up very slowly at first. And then it starts at that bend, that's when it starts to increase very quickly. And the jump to get from level 4 to 5 is huge because that graph is curving or bending upwards very, very quickly. And it's for that reason that the designers of the game decided to make each of these creatures give you different amounts of experience. Because they do recognize that, hey, you could get to 225 experience just by killing 15 rats. And they want to make sure that you are not just stuck in the first level, killing the rats, getting the maximum level, and then, moving all the way up to kill anything you want very easily. They want you to experience the whole game. And so in the third game, what they decided to do was to give you very small amounts of experience for the rats. Now that is enough, of course, to get you to level 1, maybe even to level 2. But it very quickly starts to become really, really boring moving past there, right? You have to kill so many more rats to make the jump up to the next level. Whereas if you go to the next creature, they start giving you more and more experience. Balthasar's Gate 3, its level progression, is an example of something called an exponential relationship. And that's what we're doing in this unit, right? We're learning all about exponents. In this exponential relationship, I can rewrite the amount of experience required. Instead of writing it as numbers, I can express it as a power of 3. And remember, a power is something, a big number, that's your base, and then an exponent. And when I say powers of 3, I mean 3 is the base. The first one is really easy. How do I express 3 as a power of 3? Well, 3 to the power of 1. That's 3 multiplied by itself just once. That gives you 3. What about 9? How can I express 9 as a power of 3? 3 to the power of what gives you 9? That would be 3 times 3, right? In fact, if I started at 3 and I multiplied by 3 one more time, so 3 times itself 2 times, that would give me 9. So I could write it as 3 times 3, which is the same thing as 3 squared. How would I write 27 as a power of 3? Well, I would just need to recognize that, hey, if I started at 9 and I multiplied that by 3, I would get 27, right? So because 9 times 3 is 27, and remember, 9 was 3 times 3. Another way I could write 27 is starting at 3, 3 times 3 times 3. In other words, 3 multiplied by itself 3 times, 3 to the power of 3. How can I express 81 as a power of 3? Just recognizing that 27 times 3 would get us 81. So if I started at 3, 3 times 3 times 3 times 3, in other words, 3 times itself 4 times, gets us 81. To get 243, again, I can multiply by 3 once more. In other words, if I start at 3, 3 times 3 times 3 times 3 times 3, 3 multiplied by itself 5 times could get me 243. So if I want to change these from expressing them as numbers to expressing them as powers of 3, I could do that. I guess the next question becomes, what do you notice? As the levels increase, let's examine the powers of 3, and what do you notice? Notice that the exponents are all also increasing by 1. That's why we call this an exponential relationship, because the variable that's, when we change the independent variable, that independent variable is in the exponent of a power. And as that exponent increases, we can see that the XP required is increasing way faster and faster. It starts out increasing very slowly. The graph is very flat, and then it ends up going up really, really sharply, really quickly. This is one way I would write this exponential relationship. If x was, as x increases 1, 2, 3, 4, 5, the y values, or the output of this relationship, is simply 3 to the power of whatever that x value was. 3 to the power of 2, 3 to the power of 3, 3 to the power of 4 when x was 4. When x is 5, it's 3 to the power of 5. So the y value is always going to be equal to 3 to the power of whatever that number is for x. How did I know the base was going to be 3? Well, that is the number that we are multiplying by each time, right? That is 3 right there. We keep on multiplying 3 by itself x number of times. And that's what exponential graphs are all about. Exponential relationships. They create a graph that is very flat on one end and very steep on the other end. For example, it might look like this, or it might look like this. The algebraic form, in other words, the equation of an exponential relationship, is y equals a times b to the power of x. Remember, the exponent of x, it only applies to b, it does not apply to a. So we always have to evaluate the power first, and then we multiply by a. What is a and what is b here? B can be any positive number, right? It could be greater than 1. This says b is greater than 1. If b is greater than 1, then we're multiplying by a big number again and again and again. What's going to happen is our y values are going to get bigger and bigger and bigger very quickly, just like we saw in our graph. But b could also be a positive number that's very small. If b is between 0 and 1, like for example 0.5, what happens if you multiply a number by 0.5 repeatedly? For example, if we had 3 times that base, if that was 0.5, it would become smaller, it would become 1.5. If we multiply it by 0.5 again, it gets even smaller to 0.75. And so if this number, if this base is a small number between 0 and 1, then the graph will look like this. This is called exponential decay. It's decaying. And remember when an animal dies in the wild, its body decays. It becomes into nothing, right? It gets reduced as it gets absorbed by the soil and stuff. This is exponential growth. When the number is bigger than 1, the original value, the initial value, starts growing more and more and more. When you multiply a number by, for example, 2, every time you multiply by 2, it gets bigger and bigger and bigger. And that's the base of this exponential function, or this exponential relationship. The a value is the initial value. That is the number that you start with. And then once you start with that, then you start multiplying. Every time you increase this x number up here, so if this is the x-axis, every time you move to the right, or every time x increases by 1, remember, what does that do? What is an exponent telling you to do? It's telling you to multiply the base by itself that many times. So every time you increase the number of times by 1, then the y value has to get multiplied by the base one more time. That base is called the growth factor if it's bigger than 1, or the decay factor if it's less than 1. And the final part that you need to know about exponential graphs so far is that imagine, no matter what this base is, remember that anything to the power of 0 is equal to 1. It doesn't matter what the base is, if it's a small number, it's a big number, b to the power of 0 is equal to 1. So if x is 0, then b to the power of x will be 1, and a times 1 will just be a. So when x is 0, that happens right here at the y-axis. When x is 0, the y value will always be a. So that is always going to be your y-intercept. Let's do a quick example here. And this is where exponential graphs are actually super useful for every single person in their day-to-day life. You may think about borrowing or investing money at some point in your life, and to do that, you really need to understand that debt or investments grow exponentially. So in this example, one share of Lariat Studios, this is the company that created Balthazar's Gate 3, one share of the company is like saying we took the ownership of the company and we split it up into like a million little pieces. And if you want, you could buy one of those pieces. You would give the studio $100 in 2010, and then you would own a piece of the studio that created Balthazar's Gate 3. Now that studio is very successful. It's created all of these wonderful games, and that was in 2010. So that your one little piece of the company is growing in value because the company is becoming more and more valuable. Other people are saying like, whoa, I want to own part of the studio. And every year they're willing to pay you 10% more than what you paid. So your share was worth $100 in 2010. How much was it worth in 2011? And eventually we'll extend this to find out how much is it valued at in 2023. So after 1 year, in 2011, the value of your share is 110% of its initial value. It kept all $100 of its initial value, right? But it grew by 10%. So if something grows by 10%, then its current value is 110% of what it used to be. So I'm going to take this and I'm going to convert it into a mathematical statement. After 1 year, so the value of your share after 1 year, this is not multiplication, I'm just saying the value after 1 year is, and that, when we convert is to a mathematical notation, we use the equal sign, worth 110%. And remember, how do we convert percentages into math? We just turn them into decimals. So we divide it by 100. That's 1.10. Of, what is the mathematical symbol to represent of? Multiplication. And its initial value was $100. So after 1 year, the value for share, the value at 1 year is 1.10 times 100. And that, if I evaluated this, I can find out that, it would be worth $110 after 1 year. After 2 years, this is what's wild about exponential growth, is that it's not going to grow by another $10. It's going to grow by 10% of what it used to be 1 year ago. Each year it grows by 10%. And so it's not going to grow to $120. The value after 2 years is 110% of its previous value of, and its previous value is 1.1 times 100, or $110. So you can see here that we started at 110. That was our initial value. And then we multiplied by 1.1. And then we're multiplying by 1.1 again. After 3 years, what's going to happen? The value of the share after 3 years is going to be 1.10 times its previous value. And its previous value, again, is not 100. It's all of this, 1.1 times 1.1 times 100. And so you can see here, we started at 100, and we're multiplying by a number again and again and again. And so the value of this share is going to start increasing slowly at first, just like we saw in our exponential graph. And then it's going to start increasing very, very quickly. In fact, the equation that I would create out of this, notice that I've got, after 1 year, I multiplied by 1.10 one time. After 2 years, I multiplied by it 2 times. And after 3 years, I multiplied by 1.101, 2, and 3 times. So the value always seems like it's going to be 100 multiplied by 1.10 to the power of n. That would describe what is the value of one share, V, n years after 2010. So in 2023, if I want to find out what is its value in 2023, well, that is 13 years after. All I have to do is replace n with 13. And that gives me about $345.23. This is how many people save money for their retirement, or save money so that they don't have to work as hard. Because what happened here, you started with $100 in 2010, and you gave it to this company. You bought one share, and 13 years later, you sold that exact same share. You did not do any extra work, but you sold it for an extra $245 of profit. Isn't that crazy? That you can do that and not have to do any work for that $245? This is the power of investing. And in fact, if I were to take this equation and put it into a graph, this is what it might look like. Notice this graph is exponential. It started increasing kind of slowly. And even after 13 years, I got $245 in profit. But what did we see happens to exponential graphs? Even though they start increasing slowly, as they get further and further, they start increasing faster and faster and faster. That bend is going to make the value start increasing really, really quickly after 40 years. In fact, after 40 years, that same share that used to be worth $100 is now worth $4,525.93. This is the power of exponential growth. And we need to understand this really, really well if we want to make sure that we are not working until we're 75, 85 years old, well past the age that our body is going to allow us to work, so that we can retire comfortably at a younger age and start enjoying our later years. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.